Hello, everybody. Uh, Even though classes have ended, I wanted to have a short session now talking a little bit about synthesis using the aromatic substitution reactions. And I want to divide up my comments into a section dealing with the common pitfalls, and then some synthesis problems, and then talk about the Sandmeyer complex of reactions. So first up on my agenda is to talk about some common errors that are made with aromatic substitution reactions. Okay, so let's talk about common mistakes with aromatic substitution. So the first common mistake that I see is the failure to appreciate the limitations of some of these reactions. And the one that sticks out most in my mind is that of Friedel-Crafts alkylation and Friedel-Crafts acylation. And these reactions are important because these are carbon-carbon bond-forming reactions. And when we're doing a synthesis problem, frequently we are going from a molecule that has fewer carbon atoms in the starting material to more carbon atoms in the target molecule. And so we have to make carbon-carbon bonds using aromatic substitution. And that's where the Friedel-Crafts alkylation and Friedel-Crafts acylation come into play. Okay, so first common mistake is that with Friedel-Crafts alkylation. All right, and Friedel-Crafts takes an awful long time to write, so I'm just going to abbreviate this FC with Friedel-Crafts alkylation. It's important to keep in mind that the reaction is a carbocation mechanism or involves carbocation intermediates, and you can and so that means that rearrangements are possible. So, for example, if we wanted something like this, if we started out with benzene and our target molecule would be that. Okay, so there's our starting material, there's our target. So the most common mistake that people would make would be to go from here and the and use this 1-chloropropane. And so remember, in these aromatic substitution reactions, the benzene ring, that's the nucleophile. The carbon atom that bears the leaving group, that's the electrophile. The electrophile is here. And so what the misconception is that the nucleophile will come in and replace the leaving group. So it kind of looks like an SN2 reaction in many ways, where the leaving group is gone, and what has taken the place of the leaving group? The nucleophile, and in aromatic substitution, benzene is the nucleophile. Okay, but this is not going to work because the reaction involves carbocation intermediates, and so this guy, when it forms a carbocation, is going to rearrange. If you take off this Cl, you get a primary carbocation, and that's going to rearrange to a secondary carbocation, where we're remembering that the rearrangements, carbocation rearrangements, happen when you can go from a less stable to a more stable ion. So I'm going to put a big question mark here to show that that is not going to, this target molecule will not be formed. And instead, what does happen is this thing, when we add the this 1-chlorobutane to it, it's going to rearrange to form that as the major product via a rearrangement. So that's something that we have to be wary of when we're using this Friedel-Crafts alkylation, is that it's a reaction mechanism that involves carbocation intermediates, and so the carbocations can rearrange. Okay, so that's a common mistake. Let me show you how to fix it. So if we want to make this target molecule, what we need to do is indirect alkylation. We can't alkylate benzene directly by a Friedel-Crafts alkylation, so we have to use an indirect method. Okay, and so that indirect method is going to be acylation, followed by the functional group interconversion, in which the carbonyl group is converted to a methylene. And so that's going to be using Wolff-Kishner or Clemenson or those types of reactions. So the fix is to take to put this chain on using an acyl chloride that has the very same chain that you're trying to put on the benzene ring. So I'm trying to put on a straight chain of 4 carbon atoms. I'm going to use this acyl chloride that has that straight chain of 4 carbon atoms that I want to add to the benzene ring. But notice it's an acyl derivative. And then I'll have, I'll use aluminum chloride as the catalyst. And not really managing space here too well. And so that's the nucleophile, that's the leaving group. It kind of looks like an acyl substitution where the leaving group is gone and the nucleophile has taken its place. So we get this. We get that. And now we need to reduce that carbonyl to a methylene group. And here we could use Wolff-Kishner or Clemenson or something like that. And so this is the fix for alkylation, in which the direct alkylation might involve a rearranging carbocation. So here we would use something like KOH, water, heat. That's Wolff-Kishner, and so that is the fix for these alkylation reactions that involve a rearranging carbocation. Now, if you're trying to make a molecule where the carbocation is not going to rearrange, then this isn't a problem. This you wouldn't have to alkylate, you wouldn't have to acylate and then reduce. Okay, so I'll show you an example of something where the rearrangement is going to be very unlikely. And that's going to be something like, if we start out with benzene, and we want to put on the tertiary butyl group, we want to put on that group, just using the Friedel-Crafts technology, what I would probably go for is something like that in the presence of aluminum trichloride. And when this Cl comes off, it's going to make a tertiary carbocation, and that tertiary carbocation is not going to rearrange to anything more stable, so that's a go. All right, so that's going to be a successful reaction. Okay. Another mistake that people make with Friedel-Crafts alkylation is that FC alkylation frequently is subject to over alkylation. So imagine you start out with something that looks like this, benzene, and you want to put the ethyl group on there. And so you'll put you'll use this ethyl chloride, and the chloride is not going to rearrange into anything more stable. So you're going to get a primary carbocation, and that primary carbocation can't rearrange to anything more stable in this case. And so you might think, well, this reaction is going to be great. It's going to make that. But no, unfortunately, it won't. Because the alkyl group is an activator. And so the product here is more activated than the starting material. So that if you can imagine a beaker in here, in which you have, let's say maybe 2 benzenes, right? Of course, you won't have 2 benzenes. You'll have 10 to the 23rd benzenes in here. And maybe you have 2 ethyl chlorides in here. And then you have some aluminum trichloride catalyst. It's important to remember that you have 10 to the 23rd of these molecules, and they don't all react at the same time. Remember GenChem, remember the Maxwell-Boltzmann distribution. You have some molecules that are very energetic, that are going to have enough energy to overcome the activation barrier, and then you have some molecules that don't have the enough energy to overcome activation barrier. So all of these molecules do not all react at the same time. You have 10 to the 23rd of them in a beaker, in a lab somewhere. They don't all react at the same time. So what we can imagine here from this little simple-minded drawing is that, let's say this guy reacts. He's made ethyl benzene. The other benzene has not reacted yet at all, because remember, all of these molecules don't react at the same time. And now the remaining ethyl chloride is choosing between a molecule that has an activator on it and a molecule that doesn't have an activator on it, because the alkyl group is activating. So who is this guy going to choose? He's going to choose the more reactive benzene than the less reactive one. So that the next little naive little picture I could draw here would be that the guy that already underwent alkylation is going to undergo alkylation a second time. So this is not the recipe for making ethyl benzene. This is more like the recipe for making something like maybe something like that, right? Or maybe even worse, maybe something like that. See, it's over alkylation because the product of the reaction is more reactive than the starting material, and all these molecules don't all react at the same time. So that's another common mistake that is done. And the fix here would be, again, use this Friedel-Crafts acylation, because the acyl group, that carbonyl group, is a deactivator. So there is no danger of over acylation, but there is this danger of over alkylation. Okay, sticking with Friedel-Crafts again, more common mistakes that are made with this reaction in the synthesis problem would be that the benzene, the aromatic molecule, the nucleophile, which functions as the nucleophile, can't have any deactivators. Because the Friedel-Crafts electrophile is not reactive enough. So for example, something like this. All right, so I learned my lesson about acylation is a good alternative to direct alkylation. So I'm going to try that here. So there I have a nitro group, right? and I'm going to acylate the nitro group. I'm going to acylate this nitrobenzene. And so nitro is a meta director. I'm thinking that the product is going to be this, right, where the pre-existing nitro substituent directed the incoming electrophile to a meta position. And so that would be the product of the reaction, right? Wrong. Because the nitro group is a deactivator, and the benzene ring that functions as a nucleophile cannot be deactivated. So what actually happens here, is no reaction, or at least no Friedel-Crafts reaction. So that's important to keep in mind as well, that the benzene ring cannot have any active deactivators on it. Aromatic molecule can't have any deactivators in Friedel-Crafts reactions, whether they are acylation or alkylation. Okay, more mistakes with this reaction. Another frequent mistake is that this molecule here, people love to use this molecule, right, in a Friedel-Crafts acylation. This thing does not exist. It's simply too reactive. If you cover up this side of this molecule, it's an aldehyde, and aldehydes are very reactive for steric reasons. If you cover up this side of the molecule, it's an acyl chloride, and those are very reactive. They're at the very top of the reactivity ladder. So please don't use this guy. The people that grade your exams will mark you off. This thing does not exist. I'm just telling you that. Okay, so those are some common mistakes with Friedel-Crafts alkylation and acylation. And I told you something about the fix. Let's look at another kind of reaction that has a lot of mistakes and misconceptions associated with that, and that is nitration. Common mistakes with nitration. This reaction usually works pretty well, but it does have its pitfalls. And so I'll show you the major pitfall here. HNO3, H2, SO4 predict the product. So I think we talked about how the NH2 group, the atom directly bonded to the benzene ring, has an unshared pair of electrons on it, and these types of substituents are orthopara directing, and they are strongly activating. These are the reaction conditions that put the nitro group on the benzene ring. This is an orthopara director. You're thinking that the major product is going to be the para-substituted para-nitroaniline. And so you might think, well, that's the product. Well, no, it isn't. That's not what happens. What actually happens, believe it or not, is that nitro substituent goes meta to something that started out as an orthopara director. And you see that positive charge that I put on that nitrogen atom? Well, this explains what happens. Is that amines, these are bases, right? This is an extremely acidic medium here. So this nitrogen atom is a base. And so what is going to happen is that that amine functionality undergoes protonation to give you that. And so the acidic conditions of nitration have converted the amino group to an ammonium group. They have converted an orthopara director to a meta director, and that is why the nitration occurs meta to that pre-existing substituent. And so now all I have to do is take this guy and add some kind of base to it, a base that is stronger than the mean. So for example, if I were to take this guy and react him with potassium hydroxide, right? That's a much more powerful base than the amine. So that is going to strip the proton away from that nitrogen atom, and my final product is this. Okay, sorry, this got scrunched up here. So it looks like the meta director, it looks like the ortho-para director produced meta substitution product. Well, it didn't, and it did, because the first step of this reaction would be the protonation of that NH2. So this is something else that has to be, you have to be careful with, is that this NH2 group is a base, and so if it is subjected to acidic media, it is going to undergo transformation to a meta director. And the very same thing happens once again with Friedel-Crafts alkylation and acylation. So going back to those reactions, of which there are a lot of limitations. So imagine if we were to start out with this guy, and we learned our lesson, and we know that acylation and reduction is frequently better than direct alkylation. So I'm going to apply that lesson here. I'm going to add this acyl, I'm going to acylate, and this is an ortho-para director, and it's strongly activating. And so I'm thinking, well, the product of this reaction is going to be this, right, where the incoming electrophile is directed to the para position as the major product. But once again, this is going to fail. This doesn't happen. And it's for the very same reasons that we talked about with nitration, in that the nitrogen atom is a base. I don't see any H plus anywhere. I don't see any H2SO4 or HNO3. But this guy, aluminum trichloride, this is a Lewis acid, right? It's not a Brunstad acid. It's not a proton acid. It's a Lewis acid. And so what this AlCl3 does is it coordinates with the nitrogen atom, the electron pair on the nitrogen atom, to produce this Lewis acid, Lewis base complex. And now what we see is that the atom directly bonded to the benzene ring has a full positive charge on it, and that this is a strongly deactivating meta director. And as we said before, the Friedel-Crafts complex of reactions don't happen when a meta director is present on the benzene ring, or a strong deactivator is present on the benzene ring. So this is not what happens. What actually happens is no reaction. Right, so this is another limitation of the Friedel-Crafts reaction, where you can't put is that this NH2 group, this naked NH2 group, or any kind of amine on here is not going to be able to undergo this Friedel-Crafts acylation. Okay, so those are just a couple of common pitfalls. So now let's try some synthesis problems, just of various degrees of complexity. So I guess the most entry-level kind of synthesis problem that we would be contending with would be, say, for example, the synthesis of fat. Okay, so how would you make this 1-bromo-4-nitrobenzene? So it's obvious what happens, or it's obvious what has to happen. is that you have to put bromine on the benzene ring. That's going to be a bromination using Br2 and some kind of catalyst. Right, that's how you put bromine on the benzene ring. And this guy, well, that's just the product of nitration, HNO3 and H2SO4. It's going to be a two-step synthesis, but the crisis here, the challenge is here, what is the correct order of steps? Because is it a nitration first and then a bromination, or is it a bromination and then a nitration? So that's something that we have to keep in mind when we're doing synthesis with aromatic compounds, is that the order of events is quite important. So what do I do first? Do I brominate or do I nitrate? Yeah, I would brominate first. I can't nitrate first because nitro is a meta-director. And so if I nitrate first and then brominate, I'm going to get the wrong regioisomer. So if I take this guy and nitrate, and then brominate, I'm going to put the nitro group on first, and then the nitro group is a meta-director. And so the product of this synthesis would be this 1-bromo-3-nitro benzene, and that's not what I want, right? So these are the right steps, but they're just in the very wrong order. So the correct order would be bromination. That puts on the bromine, that's an ortho para-director, and then nitrate. So, this is pretty important thing to keep in mind is what the order of steps would be. Okay, so with this simple example out of the way, let's try something a little bit more challenging. What about if we wanted to go from this guy to this one. Okay, so what would be the steps here? Once again, it's a two-step synthesis, but what is the correct order of steps? Do I put the fishtail on first, or do I put the nitro group on first? Oh, I would put the fishtail on first, because this is an ortho para-director. The major product when we're dealing with an ortho para-director is nearly always going to be the para substitution product. So it would be a mistake to nitrate first, because the major product in that case would put the nitro group here. So the correct order of steps would be first to put on this fishtail. And to put that fishtail on, I'm going to use Friedel-Crafts alkylation, right? This Cl comes off. You get a carbocation here that's secondary. It can't rearrange to anything that is more stable, so that the isopropyl fishtail is added. And now we have to carefully consider this, and now we know we need to nitrate, but that's an ortho para-director, and that's an ortho para-director. How do I know that the nitro group is going to go on there reliably? Well, the way I know that is that this is an ortho para-director class 2. This is an ortho para-director class 1. And so the more highly activating class 1 beats out the less activating class 2. And so this guy I could nitrate and have no worries about where that nitro nitro group will go. So I guess what I'm trying to tell you is that in these synthesis with aromatic compounds, frequently we have to consider the product of the previous step and make sure that it checks out in terms of the ortho, para, or meta directing capabilities, and make sure that if it's in a competition with another group, we have to carefully monitor that. All right, so let's try something else. Now let's look at a synthesis where we're not just putting on this, that, and the other substituent, but let's look at a synthesis in which we have to transform a pre-existing substituent into another functional group in order to carry out the synthesis. So this is a very common occurrence as well. If I start out with methylbenzene and I want to make this guy, all right, so what would be the steps there? So obviously that nitro group is put on by nitration. The bromine is put on by bromination. But I see that that methyl group has to end up a carboxylic acid at the end. So, it's a little bit more involved synthesis. Okay, so there's that methyl group. So it's an ortho-para director. So I see that I'm not going to brominate first because the para position is open here. And so if I brominate first, I'm going to put bromine over here in the para position. I don't want that. So I guess the molecule is telling me that the first thing I need to do is to nitrate, right? And that puts the nitro group exactly where I want it to be. Okay, and so now that's a meta director class 3. That's an ortho-para director class 2, so that the class 2 is going to win, right? This is class 3. This is class 2. The class 2 is going to win. It's saying send the ortho, send the new substituent ortho and para to where I am. The para position is blocked, so the ortho position is going to be the only available site here. And so now I would brominate, and that reaction looks like it's going to work okay. So I would get this. And now, how do I transform the methyl group to the carboxylic acid group? And this is what I'm trying to explain right now, which is frequently these synthetic reactions involve transformation of pre-existing groups. So if you remember how to go from a carboxylic acid, from an alkyl group to a carboxylic acid group, that would be that KMNO4, or chromic acid oxidation. So I would use KMNO4. That would be my first step. It's important to remember that this oxidation employs basic conditions. So if I want the carboxylic acid, I need a workup step with aqueous acid to put the proton back on. So this KMNO4 oxidation, that's a very frequent transformation of a pre-existing group. So it would be totally wrong to do this reaction first, right? Because if you oxidize this methyl group to a carboxylic acid as the first step, you've put on a meta director, and now there's not going to be any way to put the nitro group on in the correct orientation. So again, the order of the steps here are critical. It's essentially 3 steps. It's a nitration, it's a bromination, and an oxidation. But you can't do them in just any order. You have to make sure that the substituents that are already on the benzene ring have the correct orientation for the next step. Let's talk about this reaction a little bit because we haven't had a chance to talk about it, and it's a frequently occurring transformation. You need for that KMNO4 oxidation, you need at least one benzylic hydrogen. And remember, benzylic means not part of the benzene ring, but directly bonded to the benzene ring. So a benzylic hydrogen would be that, right? This guy here. He's benzylic. He's in a benzylic position. He's not part of the benzene ring, but he's bonded to a carbon atom that is directly bonded to the benzene ring. All right, so let me ask you here, what would be the product of this reaction? And remember this KMNO4, these are basic conditions. It's not always written that it is, but it is. So what would be the product here? Are you going to get oxidation? Oh my heavens, yes. Because that's a benzylic carbon. There's a benzylic hydrogen there, at least one. So this carbon is going to be oxidized. There's another benzylic carbon down here. Are there any benzylic hydrogens there? Yep, there's at least one. In fact, there are two. So this carbon is going to be oxidized. And so the product here is going to be this benzene 1,2-dicarboxylic acid. And what happened to the rest of these guys? Oh, they got oxidized off as well, but they come out as molecules of carbon dioxide and water. So those just bubble away, right? And that's one of the things that is providing these basic conditions. So in this reaction, what is happening is the oxidation of the benzylic carbon, right? Not the oxidation of the whole substituent that's on the benzene ring, but only the oxidation of the benzylic carbon. All right, so let's see. Let's try another one.
I have a question about that.
Yes.
If you use H2CrO4, do you need the workup step or no?
You don't, because that's going to provide the acidic conditions already.
Okay, thank you.
Okay, so maybe something like this. How about this? What would be the product here? Oh, I see a lot of benzylic positions. And remember, this KMNO4 reaction oxidizes the benzylic carbon. So I see a lot of benzylic carbons, but what I'm really looking for is a benzylic hydrogen, at least one on those benzylic carbons. So there's a benzylic carbon. Are any hydrogens there? No. So this ring is stable toward oxidation. What about a benzylic hydrogen down here? No. So nothing's going to happen to this ring. It's just going to survive intact. But that's a benzylic carbon with a hydrogen. That's a benzylic carbon with a hydrogen. That's a benzylic carbon with a hydrogen. All of these are going to be converted to that carboxylic acid functionality. And the rest of these carbons, they just get thrown away. They just get oxidized off to molecules of carbon dioxide in a very complicated mechanism. So the product here is going to be carboxylic acid there, carboxylic acid there, and carboxylic acid there as well. And what happened to these other two rings? They just got thrown away. They just bubbled away. Okay, so Now let's talk about this brilliant, complex reactions of the Sandmeyer. Okay, so these are the Sandmeyer reactions. So that is pretty well exemplified by the following synthesis. So how would you convert benzene to this 1-bromo-3-chlorobenzene? So do you notice something that's very strange about the target in relation to the starting material? Do you notice something that's very, very odd? What would that be? Why does this target molecule kind of look very odd if you're trying to make that from benzene? Because Br is an ortho-para director, but I need the Cl meta, and Cl is an ortho-para director, and I need the Br meta to where it is. So this is where the Sandmeyer reaction comes riding in on its white horse, because the Sandmeyer reaction frequently allows you to add substituents to the benzene ring in quote unquote unnatural orientation. Okay, so let's go through how we would do something like this. Okay, so what I'm talking about now are the steps in the Sandmeyer reactions, and they are so see, to go from here to here, it's going to be quite involved, lots of steps. So let's go through. All right, so the first thing I would do is I would nitrate benzene ring, and I could I'm going to put the nitro down here at 4 o'clock. I also could have put it here at 12 o'clock. It's obviously the very same molecule. And so maybe you're wondering, well, why the heck am I'm trying to put Br and Cl on the molecule. Why would I nitrate? Well, this is where the Sandmeyer reaction comes into play. This nitro group this is a meta director, right? And I need these two substituents to be meta to each other. So by putting on this nitro group, now this guy can undergo a reaction that's going to set up the meta orientation. So now I'm going to brominate. Now I'm going to brominate, and that nitro group is giving me that meta orientation that I want in the target molecule. And now this nitro group can be reduced using hydrogen or lithium aluminum hydride. The nitro group can be reduced to the NH2 group. So I could use lithium aluminum hydride or hydrogen and a catalyst. And a long time ago, we talked about how oxidation means more bonds to oxygen, and how reduction means fewer bonds to oxygen and more bonds to hydrogen. So lithium aluminum hydride or hydrogen reduce the nitro group to the NH2 group. And it turns out that the nitro group on a benzene ring, frequently, this is pure magic thanks to the Sandmeyer reaction. Okay, and so now this NH2 group reacts with sodium nitrite and some kind of acid, right? And see this little 2 here? Oh, this is very important, right? If you write NaNO3, oh, you're going to get that marked wrong, right? So this has to be NO2, sodium nitrite, and acid. These guys get together to make something called nitrous acid, which is HNO2, not HNO3. And a lot of times you see this written kind of like a condensed structure. It kind of looks like HONO, but it's actually nitrous acid. And these conditions convert the aromatic amine to the diazonium ion. Right, and that NH2 is a excellent leaving. Right, so this is the first stage really of the Sandmeyer reaction. All of this has just been trying to set up this relationship. And this NH2 can be displaced by nucleophiles, right? And one of the, frequently they're copper-based nucleophiles. So I would take this and I could react that with copper 1 chloride, where the Cl is now the nucleophile, and the NH2 is the leaving group, and it replaces that NH2 plus with Cl. And so it took 1, 2, 3, 4, 5 steps to enforce this unnatural regiochemistry, but this is what the Sandmeyer reaction is really good for. Okay, so let me see if I have another little example here. Oh. Okay, so how would I synthesize this compound from benzene? Well, once again, what I'm noticing is that a natural regiochemistry. I have two orthopara directors, but they have to be meta to each other. That is your big clue that that Sandmeyer reaction is going to be in play. So what I would do here is first nitrate. Right, there's my meta director. I need Cl here, so I'm going to go ahead and chlorinate. And now I get into those Sandmeyer reactions where that NO2 group on a benzene ring, this is pure magic, right? Using those Sandmeyer reactions, I can convert the NO2 on the benzene ring to all kinds of different substituents. Professor Porco showed a slide showing the various Sandmeyer reactions. All right, so what I would do first here is now I have to reduce the NO2 to NH2. So I have NH2 here. And then I diazotize. That puts this diazonium ion there. And that NH2 group is an excellent leaving group. It can be knocked off by nucleophiles. I need to add OCH3. So the most convenient nucleophile to use here would be methanol. Methanol's a nucleophile. If you wanted overkill, if you need to engage in overkill, you could use CH3O minus, but that's not really necessary. Okay, so these are just some exemplifications of using those Sandmeyer reactions. Well, That's all I have for you today. And I guess if there are no questions, I'll see you down the road.
Professor Rubio, I have a quick question.
Uh-huh.
So with this Sandmeyer reaction, the one that's on the board right now, could we do it the other way around where we chlorinate first and then, or yeah, sorry, the other where you put the OCH3 first and then chlorinate through the Sandmeyer?
That would be exactly what you don't want to do because OCH3 is an orthopara director. So if you stick the OCH3 group on first, how are you ever going to get the Cl to go?
Oh, sorry. Sorry. If you put the NO2 and then instead of chlorinating, put the OCH3 on.
And what reaction is going to put the OCH3 on?
Okay. Okay.
Right? Because you see, the OCH3 goes on because we created this diazonium,
Okay.
this N2 plus that gets replaced by the OCH3. This guy doesn't have the NH2 on it yet.
Got it. Got it. Okay. Thank you.
Anything else? Very well. I'll see you down the road. Bye-bye.